Hello students, and welcome to the continuing lesson on parametric equations. And we've seen from the previous videos and the previous examples how parametric equations can be used to write linear equations, to simulate the motions of a line. Okay, now in this video we're going to talk about how do we simulate motions with a curve, which is what's really interesting and the true power of a parametric equation. But before we get into that, we have to prove one identity, and this identity says cosine squared of theta plus sine squared of theta is equal to 1. Okay? And just a quick note on the notation of this. I'm not sure whose idea it was to put this square here, but it's a little bit confusing, so let me just clarify that. When you see cosine squared of theta, that's the same thing as cosine of theta, and then the entire thing squared. Okay? Same thing for sine. So this notation here just means take the cosine of theta and then square it. Take the sine of theta and then square it. Add it, and you should always get 1. And we are going to prove this. First, let's just look at the circle, the unit circle, and we can see how this can be helpful to us. Okay. So if I have let me draw a better circle here. So if I have a decent looking circle here on the XY coordinate plane, and I have some point on the circle, I don't know what those coordinates are, so we can just call them X and Y. And I know that the radius of the circle is going to be equal to R. One other thing that I do know is that this point XY, we can use it to make a right triangle with the length of the base equal to x, because that's how far we went over in order to get to the point, and the height of this triangle equal to y. And then the angle of rotation, the angle inside of this circle, this triangle here, we will just call that theta. And our goal here is to show that cosine squared plus sine squared equals 1. Well, one of the things that we know and we can start with in this proof is we know that, and I'll just write out these steps here, we know that cosine of theta is equal to x over r. Okay? So this is just adjacent over hypotenuse. Okay? The adjacent side is x, the hypotenuse of this triangle is r. And if we extend this idea, if we square everything on both sides, cosine squared equals, I'm just going to get x squared over r squared. Okay, so if we just did this and we square both sides. And remember, I want to eventually get to this point right here. And we can do similar things with sine. I know that sine of theta is equal to y over r, and that's just opposite over hypotenuse. So this is just opposite over hypotenuse. Okay. And then we square both sides, and we get sine squared theta equals y squared over r squared. And since we're trying to prove the statement, let's put these two equations together. Okay, so in step 1, step 2, step 3, we're going to add the two equations. Okay, so we add the two items on the left side. We get cosine squared of theta plus sine squared of theta, plus sine squared of theta is going to be equal to the sum of the right side. So that's x squared over r squared plus y squared over r squared. And just to simplify the work a little bit, we know that it's the same denominator. Okay. So we can just combine those two on the right side here. Cosine squared theta plus sine squared of theta is equal to x squared plus y squared over r squared. Okay. So nothing special there, but our goal is to somehow show that this left term here, the right term, the right-hand side, is equal to 1. And the way we can get this to happen is if you look back into the picture here, by the Pythagorean theorem, x squared plus y squared equals r squared. So steps 1 through 4, we've worked primarily with the trigonometric ratios. Step 5, we are going to use the Pythagorean theorem. And there's a reason why this is called the Pythagorean identity. It's because it uses the Pythagorean theorem. So in step 5, I know that x squared plus y squared equals r squared. Okay? You have one side of a right triangle, you have another side of a right triangle, you have the hypotenuse. So the Pythagorean theorem tells you this. And finally, in the last step, we just make a substitution. So I write my reasons on the left side here, substitute. I have x squared, y plus y squared. I have x squared plus y squared. I know it's equal to r squared, so I can just substitute that in there. So this is going to give me cosine squared of theta plus sine squared of theta is equal to, instead of writing x squared plus y squared, I can just write r squared. And my denominator is still the same. And you can see here that my proof is basically done. So if you look at step 4 and step 6, it's the exact same thing except for this one substitution that we made here. We know that x squared plus y squared equals r squared. And this is going to equal 1. Okay, and there you have it. The proof is complete. Okay? And keep this proof in mind because it's going to be very, very useful to us later on. Now, before I proceed further, one thing that I do want to do is revisit step 1 and 2 because there's something useful that can come out of there too. Revisit steps 1 and 2. Okay. So one of the most useful things that can come out of here is if I multiply both sides by r. If you multiply both sides by r, I get r cosine of theta equals x, and r sine of theta equals y. Okay, so if I take this equation, multiply both sides by r, this is what I'll get. If I take this equation, multiply both sides by r, this is what I'll get. And I just want you to keep this in mind. There are 3 major statements that we are going to be able to use here going forward. One of them is the Pythagorean identity itself. The second one is the fact that you can separate x and y into 2 equations, x being r cosine theta and y being r sine theta. Okay. So I'm going to hit the pause button right here and continue on in a different video where I'll show you how do we eliminate certain parameters and how all of this information here is related to parametric curves.